Hi guys, it's me, Siangkong. So, uh, yeah, I'm gonna go today. Just read the description, okay? Hey, I'm adjusting my setup. You know what? Actually, yep. I think this is good. So, this is the code. Just like the compile documentation. I don't know what that is. This is like a relic. So let's just keep that for now. Also, I'm having some accent slips, so just I don't know. Just expects me, bro, grammar, bro. Just expect me to do like some accent slips because this is like actually I'm gonna put my voice in a different channel. This, yeah. Now I have no interruptions. I can hear nothing. Like it's in my other this thing. My voice is in that thing, and then this is what I'm hearing. There's nothing in there. So yeah. There's no interruptions, there's no access slips, although it may I may do it sometimes, but it's not that common because there's no interruptions. So I'm adjusting it. I think I'm gonna play some music, right? Is that good? Wait. If I didn't tell you before, my mic isn't actually a mic. It comes from this thing, audio relay. Basically, my phone is the mic. Then it sends the thing into my PC. Then you can hear the audio from my PC. Oh my goodness. Oh my god. Lower it please. Yep. Hi. I'm gonna test my voice over the audio in my PC. So did I? Oh, never mind. Hopefully I didn't hopefully I didn't reveal my IP address because like this took so many takes. Okay, I need to stop yapping. Okay, play the audio. Hi. Hi. Okay, it's good. Yep. Just make it that way. Shut the fuck up, bro. I didn't mean to say that. Sorry, guys. Okay. I'm not gonna show you my personal messages, so I'm just gonna reveal my IDE. Bye. Okay. I'm back in my ID. So, let's go. So this is the temp. It's the cache. And then this is the system 17. Oh wait, I forgot my assets. I don't wanna... Actually, I'm gonna create a group. It's like yay 2. Oh, name is already in use. Pick music. Bye. I'm gonna rename my yay 2 to something like route 1. Huh? Oh. What? Oh! Okay. Yay 2. I'm gonna rename this. How though? Yay 2. What? I can't. Yo! Bro! How? Do I need to like... Do I need to like make a new thing or something? Hold on. This group called Yay 2. Yay. Window capture. Route 1. What? Huh? Ah, okay. Then go to the Dixie. Then route 2. Also window capture. I'm like layering window captures. I select it. Capture audio, capture cursor. Wait. Huh? If I do that. No. I wanted to like display my whole screen except for some windows. OBS. Wait, I'm gonna search. Chrome.exe. Okay. Air over. No way, bro. I don't have a second screen, bro. How? How? Route 2. Bruh. If I close this. Yep. Then, yay. Yep. There we go. Alright, alright. I'm just gonna see. Okay. Good. It's not capturing the other Chrome.exe. That's Facebook. I'm also gonna add the route number 3. Hold on, guys. This takes so long, bro. Route 3. Projs. Okay, good. Okay. Actually have like something to work with. Alright. I'm gonna play some music, I guess. Maybe outline. Or grayscale. Okay. Yep. No. It's not cash. I'm testing my voice. I'm gonna close. I'm gonna get to the closest possibly to the mic. There. It's been 40 minutes. My live stream hasn't even started with the project yet, bruh. Okay. No worries. Tweets. Oh, did I redo something? Oh, never mind. I thought it was okay. Okay. 185 megabytes. The thing is in 144p. 144p. Am I right? Yeah. So that it doesn't take up too much CPU. Alright. What? So, what's the first thing we need? Oh wait, boot. Let's call it boot legacy. And then let's okay. So it's in assembly. So we need like how to make a bootloader? Okay.
So make sure you hit that subscribe button and let's get started. Let's start by answering a simple question. What happens when you power on your PC? All starts with post or power on self-test. Power supply sends power to all the components. Then BIOS firmware takes control and it initializes CPU, memory and other hardware components. The post checks for hardware errors, such as checking memory and ensuring all the essential devices are operational. Then BIOS firmware code is copied from ROM to random access memory to your RAM for faster execution. Once all that is done, a search for bootloader begins. BIOS checks the boot order setting to find the boot.
Let's increase the quality. Yep, there you go. Actually, let me make like gain. What's this countdown though? Okay, volume boost. Hi. Hi. Alright.
Boot device. The firmware looks for the master boot record, which is the first 512 bytes of the boot device, also called the boot sector. Done a search for bootloader of displaying messages on the screen. What's up everyone, welcome to the new mini-series where I'm gonna teach you how to write a bootloader from scratch. In this video you will learn how boot sequence looks like, what a real mode is, and you will write your first bootable code. This series will consist of 3 videos, and by the end of it you will have a fully working bootloader that will load a 32-bit kernel capable of displaying messages on the screen. You don't wanna miss it, so make sure you hit that subscribe button and let's get started. Let's start by answering a simple question. What happens when you power on your PC? All starts with post or power on self-test. Power supply sends power to all the components, then BIOS firmware takes control and it initializes CPU, memory and other hardware components. The post checks for hardware errors, such as checking memory and ensuring all the essential devices are operational. Then BIOS firmware code is copied from ROM to random access memory to your RAM for faster execution. Once all that is done, a search for bootloader begins. BIOS checks the boot order setting to find the boot device. The firmware looks for the master boot record, which is the first 512 bytes of the boot device, also called the boot sector. It identifies it by looking at last 2 bytes, which are 55 and AA respectively. Once the bootloader is located, BIOS loads it to memory and executes the code. Now that you know the basics of BIOS boot sequence, let's talk about the real mode, which is a 16-bit mode in which all x86 CPUs start their execution. Later on they switch to protected mode, but we're gonna talk about it in the next video. In real mode, memory access is handled using segmentation. We have little over 1 MB of addressable memory in format segment offset. 16-bit segment memory access is handled using segmentation. We have little over 1 MB of addressable memory in format segment offset. 16-bit segment address is stored in one of segment registers. This is basically a starting point of a segment, and 4-bit offset value is stored in one of the general purpose registers. So in total we have 20 bits, 2 to the power of 20, so roughly
Damn.
1 megabyte. To calculate a physical
Okay.
address, you can use this equation. We are taking the base address of a segment, multiplying it by 16, which is equivalent to shift left by 4 operations. So we are sort of making space for the offset. This is like an explanation for those who don't really get the hexadecimal math, but it's okay, you don't need to know it perfectly. But anyway, to this you add an offset and you have the physical address of the exact location in memory that you want to access. You also have to know that real mode is not secure at all, and when CPU runs in it,
I did not think it would tell me that I need to prep
Bruh.
editor the day before.
Your lineup needs work. Yeah,
No
it
way,
did call
bruh.
me out.
a user program can impact kernel in such way that it can completely destroy it. Alright, so enough theory for now. Let me show you some tools that you need to install. Firstly, sudo apt install Nazem. You need Nazem. This is gonna be the compiler that we're gonna use to compile our assembly code. And the second thing is sudo apt install qemu system x86. I already have it installed, but yeah, just copy these commands, both commands from the video description, paste them to terminal, and you will be good to go. Let's go to documents. Let me make this a little bit bigger. Okay. Let's make the let's call it bootloader, CD
Okay.
bootloader, and let's type code to fire up Visual Studio Code, one of my favorite IDEs. Let me make a folder called bin to store our binaries, and a folder
Okay.
called source to store the source files. This is the sort of elegant way
Okay.
of
So we need assets. Yeah, we already have assets. We need to make another asset for this. Asset. No. Legacy and main. Okay. There you go.
of handling your projects. It is not very necessary because this is gonna be a very small project, right? But it is just good to have this habit of sorting files. Let me make a boot.asm file inside the source.
Okay, assembly. We really need to do assembly, bro. Wait, what? Source? And then... Oh, what? What do you mean? We need to put it to source. Actually, let's delete that. Main. Oh no. Put that to main because it's assembly, not source files, I guess. I don't know.
And inside the root directory, make file. Oh, it's not inside the... wait. Yes.
Okay.
Okay, file, make file. Like this.
What? What's make file? What's make file though? What? Make file. Let me try that. Wow, okay. I didn't know VS Code has that.
In root directory.
Oh wait, root directory. Okay, let's go to the root directory. Root legacy. There you go.
Move. Okay. If you have never used makefile, so this is basically a file that will allow us to compile and clean the project much quicker. It is gonna be a lot more elegant sort of way. If you need to compile
Lol.
a lot of files at the same time, it's easier to just type make all instead of compiling each file each file separately. So this basically allows us a little, gives us a little automation. But don't worry if you never used it. I'm gonna show you line by line how to do it. Okay, so let's start writing the code. We want to start with specifying that we are in 16 bits, like this, and the origin.
Okay. Bits 16. Wait, hold on. I'm gonna download an assembly thing. Assembly. Okay. Alright. What? What? Huh? What do you mean? What do you mean? Okay, maybe he's using this. Let's probably sure I'm this install. Okay. Let's write bit 16. Ah, okay.
Of our code. So we want to tell assembly, our assembly.
Origin 0x7C00
That the code will be loaded at this address. The code will start at this address. And why this address? Well, because BIOS will load our bootloader to this address memory, basically.
Ah, okay.
So start label, we want to start with CLI, which is clear.
Start CLI. Huh? Oh wait. Start CLI. Huh? CLI.
Interrupts. And interrupts are these signals
Okay.
that allow CPU to sort of change focus. So if it is executing a task and an interrupt from a keyboard, for example, is triggered, then CPU is pausing the current task. It's going to handle this interrupt and then goes back and resumes its previous activity. So
I'm moving my mic.
it works like this, but I'm gonna tell you more about interrupts later.
Wait, hold on. I'm moving my mic so that you can hear me clearly, more clearly. Yep. There you go.
Video. So let me move to the register AX, the value 0x00.
Okay. Move AX 00. Okay. Also, this is like the syntax highlighting of Roblox. Yeah. Isn't that cool?
We want to set the base of almost all the code segments, almost all these segments to this value. So now you go like this: ds ax
Move DSAX. I don't know what he's typing, bro. I'm just following. I move DSAX. Wait, let me search what DS means. And AX2 meaning assembly. Okay. DS data segment and AX. What does AX mean? Okay, they're all registers.
es ax.
Move ESAX. Okay. Move ESAX. And then
Move what else? ss ax, right?
oh wait,
SS,
okay.
ax. Move sp to
89% of
Bruh.
Filipino consumers use Google or YouTube every day.
Bruh.
Customers know
0x.
Bruh. Oh, what?
700. This is the stack pointer.
Okay. SS move SS AX, move SP 0x70 there.
Let me make it a little bit bigger. This is a stack pointer, and we want the stack pointer to point here, because it will grow downwards, sort of. So the stack will grow to the 0 from here to the address 0.
What? I don't get you, bro.
And our code is loaded from here, starts here. So you just have to imagine it, sort of. Imagine a table, and you have this 0 level, you have this 07C00 level, so our stack will grow here, and our starts here and goes up, sort of. That's
Okay.
how it looks. And after we set the stack pointer, let's type what? I forgot. STI. Okay, I have to look at my notes sometimes. STI will enable interrupts.
What?
Back. So
I see. So clears everything, and then it does this, and then it resumes. Okay. Okay. I see.
yeah, interrupts. Okay. Because this is basically also disable interrupts. Like not only clearing it, but it makes CPU not care about any interrupts. We don't want it. We don't want this setting to be interrupted in any way. And now let's move to the register SI or message.
Move SI. Move SI message.
And we don't have a message yet. So MSG is gonna be the word hello.
MSG. Hold on. Okay, MSG. The word. What? Huh? He's using single quote marks. Near or boot. There's boot. Boot success. Okay.
World. Like this, with an exclamation mark and 0.
And 0, okay. 0. Alright.
So we need to end the string with a null character. Great, actually let's make it db, dw. And
Okay. DB. What? I don't even know, bro.
That should be all for now. Okay, maybe not all for now, because now we just we did a basic setup, right? And what do we want to do now is to print this message. But there's no function like print.
Okay.
Like in C.
I see what you're doing.
F and specify your string here, right? But there is nothing like this when you
Okay.
have no operating system, you have no
Wow.
nothing. So how do you print it? Well, BIOS takes care of it. So let's take a closer look at what BIOS actually is. Basic input-output system.
Okay.
For some low-level services called functions that are very handy during boot up process. In real mode, we can access them via software interrupts. Here you can see some common functions and a little setup they require to work. And now we
Okay.
want to be able to print characters to the screen. So we're gonna use 0x10 function with A8
0x10. Basically 0xa. Oh, never mind.
register set to 0xe. Okay, so
Huh? 0xe. Display.
AH register set to 0xe. Okay, so let's make this simple loop here. Label print. We want to start by typing instruction load sb, which basically loads byte at address d,
And then print. Function. Alright. What? Low SB. Wait. Drinking water. Alright, I'm done. LC3 assembly.
ES DSSI to AL register
I don't know what you're talking about, bro.
SI. So remember this formatting that I showed you before. Segment offset. At this address
Oh, okay.
is our first letter. So
Grammarly, when you're working on yet another cover letter for that internship, and it starts to sound
CV.
after we do load SB, it will load H, capital H to AL register, and it
Oh,
will comes here.
okay.
Nice. So let's compare AL with 0.
Compare AL with the
If AL is a null character, then we want to jump to done, which is
jump to done. Okay. You should jump to done. Okay.
it's another label. Let's put it here. And in done we want to clear interrupts, and we want to halt, which basically means stop CPU.
Ah, okay. Done. Like built-in. I'm treating it as like a built-in function because it feels like it. Shall I halt? Okay.
Stop further CPU execution. I think this is a correct description. It will basically stop the execution, right? Alright, but if it is not a null character, then we want to move to the register AH, our value 0x0e. We want to
Move AH. Move. Wait, what? Move AH 0x0e. Bro, this just AH 0x0e.
int 0x10.
Int 0x10.
So we want to call BIOS to print this character.
Alright.
Then we want to unconditionally jump to print.
Alright.
Why?
Huh?
Because we need to do it sort of a couple times to print all.
Ah, okay. Okay. Jump to print.
Sentence. So, as the last thing, remember we need these 2 bytes at the end, 511 and 512 bytes.
55AA.
AA 55.
55AA.
In this order, because it is in little endian, right? So
Huh?
you need to kind of
Oh, okay. Little engine.
AA 55, of of course, when we'll inspect it in text editor, it will be in reverse. But yeah, this is just the little endian notation. So you do it like this, but there is a little catch. Actually, there is a little catch because we need to put them at this exact location. But of course, this code is not 510 bytes. So we need to put some more characters here. We're gonna do it with times 510 minus $sign minus double $sign DB0, like this.
Damn, I didn't.
And it will be.
I didn't expect assembly to be this like complex. I thought it was just like move and stuff. I didn't know it was like this. Okay. Times 5 times 510 minus $sign minus $sign. Yep. Then, oh my goodness. DB. Hold on. I'm gonna put my phone here. Oh my. Okay. Alright, just a more different setup. The mouse and the keyboard are in the same level, but it's also uncomfortable in a different way because the case, the PC is like hold on, let me try something. Whoa. Wait. No, bro, how can I position properly? Maybe with this. Alright. Okay. 0. Yep. Oh no. DB0. Right. Yep.
Space here with zeros until you reach 510. So basically, what can we do now? Go to Makefile, type all. Tab, this tab is super important here. NASM -f bin
What?
source boot.asm output bin boot.bin.
Okay, so I really need NAS. I wonder if it's available for Windows. For Windows. Oh my. This is a very incredible setup. Incredible. Oh my. No! Oh. Damn. Oh. That gave me a heart attack, bro. I almost shut my PC down. I'm repositioning my PC. Is this good? Alright. Okay, official awesome website. Stable. Hold on. Gotta turn to the original setup because this is way more uncomfortable. Alright. It's just installing. 1 minute. 1 minute left. What do you mean? Okay, whatever.
Like this. And let's make clean. Also tab, RAM.
Turn pressure.
Wait, hold on. You can save this.
Into performance. Share files and get actionable insights with AI. All in one smarter, shared, cooler space.
Dash F. Bin.
Okay, all. What? Oh. Amazon. F. Main. Dot slash. Huh? Ah, okay. No, actually no. Dot slash main dash root dot asm dash o dot. Okay, I need to louden my voice more so that y'all can hear my voice. Yep. Alright, so wait, it's installed. Huh? Why is it like, let me change this to a different thing. Window title must match other OS. Same executable. Yep. Huh? It's not showing up. It's like in the let me make a new. Ah, okay. I get it. I get it. Explorer.exe. Match style. And then why is it loading? Okay. And I'm gonna go to downloads. This thing is so slow. Alright. Yep. Run as an admin. I'm just gonna close this. What? Oh. Wait, let me see my chat. I think there's someone chatting here. Oh, there's no one. Yeah, it's a rite of passage for any. Huh? And reduce it settings using a faster encoding faster. Hold on, guys. Encoding overloaded. I think that's why it's so slow. Oh my goodness. Oh my goodness. Damn, okay. Scared it. That scared me. Alright, video. Oh. Okay. Audio video bitrate. Maybe I'm gonna turn it down to. Wait. It's 5 degrees. Alright, I'm gonna change it to 5 Mbps now. Oh. Okay. What? Recordings cannot be paused if the recording quality is set to same as stream. What do you mean? Let's just apply this thing. Code. I'm also gonna turn down like the code. Oh my goodness. OBS chill. Okay, man. It's not responding, bro. It's not responding. Nah. Codec. Let's change the codec. Ultra fast. Hardware. Okay, finally. Okay, enable custom encoder. What? Okay, I change it now. Okay, it's back to normal again. It's smooth now. The FPS is smooth, I guess. But still, it's at 100% CPU. Oh my goodness. What? Huh? It's like 61. Oh. It's Oh my goodness, what? It keeps climbing up. And task. What? What the? Bro, it's always at 100% CPU. Wait, guys. What? 74%? Nah. No. No. Oh my goodness. It's at... Okay. It's slowing down. Bro. Yo, chill with the CPU, bro. Chill with the CPU. Stop torturing Mr. Compy, bro. On video output. Okay. Go to preset. Audio bitrate, I'm keeping it that way. Apply. Oh my, chill. Chill. Bro, OBS is at 60. Stop torturing Mr. Compy that much, bro. 70%? Okay. I'm just gonna... Okay. Encoder. Switch my encoder. I already did that. Okay. Enable preview. What do you mean enable preview? Right click the preview. Okay. Enable preview. Disable. Finally. Still at... Okay. It's calming down. And then what? Bro, it keeps... Wow! I'm gonna make this 720p, I swear. Bruh. Bro, this thing, man. Hi. What? Oh. One. Exit. One. Okay. I just pressed like something in my monitor. I'm gonna activate it again. Okay, it's at a steady 50%. 56 average. Alright. Okay. Spike. Mm, 72%. I hope it's at 62. Steady rate.
So when we type make all, it will compile our boot ASM file.
Slash all dot bin dot bin dot main slash boot dot bin. Alright. Okay. Wait, hold on. 0 dB. Okay, it makes my voice louder, right? Okay, close. Encoding isn't overloaded, so that's good to know. Clean. Wait, hold on. Did I install it yet? Okay. Clean. RM dash F then dot main slash boot dot main boot dot bin. Alright, well, good.
It will clean the previous compiled file from this folder. So let's test it.
Alright, okay.
Clear unless we are in the correct folder. Just check. So make all. We have one error. Somewhere I have 31. Here. What's wrong? Oh, there should be a
Okay. Wait, I'm gonna do that too. I'm just following him, bro. Okay, I'm gonna use the terminal. Gonna show you. Coding overloaded. Okay. Disable preview. Oh my, oh my gosh. What? Bro, I already did everything. I did everything, bro. Yo. What? Huh? Oh my goodness, bro. I need a new CPU, bro. I need a new CPU at this point. My gosh. What's wrong with you, OBS? I think I'm really gonna change the FPS value. Wait, hold on. Actually, no. I think it's like this. No, it keeps. Oh, never mind. It's cooling down. Okay. Enable preview. What? It's not. Wait, hold on. Yep, okay. Oh, wait. Okay, there we go. Bro, I just... Roblox game kind, what are you doing here? Okay, I'm turning it on one by one. Okay. I think it's humble ourselves. Okay. I'm not gonna turn all the three windows viewing thing.
This is why, yes.
Okay,
Okay, so
so it created something. Oh my, it's at 100% CPU. Who's taking up the CPU, bro? What? It's not OBS, it's literally 46%. It's audio relay. Okay, audio relay. Ah. What can I do with you, bro? It's literally like the bare minimum. At least it's not like 100%. Huh? Oh my goodness. It's fluctuating. Alright. So let's go with, I will show you like the thing. So Windows Terminal. What the? What's happening? Okay, I can't show you it, so I'm just gonna work on it here. Color A for hacker vibes, just for fun. Oh. Okay, it's let's go to the directory. cd c near rs system 17. There I go. And then make all. What do you mean make all? Ah, okay. So it's only in Linux. Make all Windows. Wait. Windows. Make all. Okay, PowerShell. Oh my goodness. PowerShell. Let's run it as admin. And then Choco install make. I hope I have chocolate. Okay, I have chocolate installed. Alright. And then wait, no. Let's go to the bootloader itself. It's in boot / boot legacy. Okay. cd cd what? cd boot legacy. Alright. And then make all. I'm afraid to do this. Oh, what? Process begin. What? Error 2. Make file 2 all. What? So it's how did they make that again?
The future of work for me is working locally, but on a global scale. New flavors for soup and syrup every day. Taro custard pie.
Boot the data. Main out. SF dash F bin. What? Wait, hold on. Create process null. It failed. System cannot find the file specified. Okay, let's go. boot.asm main/boot.asm. s main. What? Let me show you. Oh my. Bin. Okay, I think we need to make like I need to reorganize this low-key. Okay, let's go. And then bin, then src. Yep, this is the source. Bin. Alright. Oh! Oh! Ah, okay. I didn't see that, but let's try again. I don't wanna redo it again. Make all. Oh my. Make all. Cannot find the file specified. Huh? What? Oh, wait.
Pressing down rm -f.
The bin. Wait, let me change this. I think it's here. It's related to that. It still cannot find the file specified. Huh? What? What? What do you mean by this? Huh? Wait. What? It's the same copy. Huh? What What's this? Wait, let me search. What's this? Okay, I'm really confused. Wait. Oh wait. Bro, why didn't I? Bro. Okay, it still shows an error. Is this a tab? Yeah, it is. I'm still confused. It isn't. Bro, what? What? Wait. I'm gonna drink water. That's F. Okay, he got lucky. I didn't. Okay, I'm just gonna ask. I'm just gonna ask like AI at this point. Hold on. Oh wait. I didn't. Okay. Move that thing. There's no technical difficulties. No way. I just. Bro. What? Hold on. I'm so dumb, bro. Let me see if someone's actually in here. Nope. There's no one. Bruh. Always the rite of passage, bro. Wait, hold on. I'm gonna sign into chat. I think it's not visible if I'm not gonna sign in. Wow. Wow. Two-factor authentication. Oh. Oh my goodness. There's no one. Let me change this. Yo, it's already tab character. Delete the spaces. No spaces. SRC. Yep. SRC exists and boot.asm is inside SRC. It's already tabbed though. I can confirm it. Wait, hold on. Yeah. I can't go in the middle. Yeah. Hold on. My goodness. You're such a pain in... So just... Wow. Wait! I'm gonna paste the thing. The air. Oh wait. Ah, okay. Nasun isn't like stalled in paths. Wait, hold on. Nasun install in path. Nasun sysdm.cpl and advanced environment variables. Oh, and then where is it? Select. Oh yeah. Okay. New. And then Nazum, where are you? Properties. Okay, files. Nazum that icon. Damn. Nazum that exe. Program files slash Nazum. Actually no. Nazum. Yep. Okay. Let's try make all again. Okay. My goodness. Move up. Okay. Move down. Okay. See program files. Nazum. Okay. Oh my gosh. Okay. Let's make all again. Still no. Term is maybe terminal start. CD rs and what is it again? 1617. Then boot and bootloader. Boot legacy. Okay. And then make all. Color A, make all. Yes! Yes! Oh my god! Oh my goodness! Oh my goodness! Oh my goodness! Oh my goodness! Yes! Yes, it created it. Oh, Mirror's boot success. Let's go. Wait, hold on. Hold on. I gotta go to the restroom. Let's go, bro. Let's go. I'm back now. I also like brought some bread to eat. Okay. Prep. I prep a bread. I'm back. And then
Okay, so as you can see, it was successfully compiled. If you go to bin, you can see we have this boot.bin. So now let's type bless, boot.bin. Bless is a very nice hex editor. You can download it by typing sudo new terminal sudo apt install bless, just like this, and it will install bless for you. So let's go back to bless, and at the bottom you can see we have 55AA exactly.
let's see. Oh wait, I deleted it.
At 511 and 512 byte. So let's test the code out if it really prints. So QEMU system.
I have walkway though. Wait, hold on. Let me see. Download this one. Oh! Let's install. What if I... Wait. What if I type this though? Oh! How convenient. I don't need to type. I just... No way. Okay. One to 5 MB of zip file. Yeah. Wow. So now folders. Yeah. How did he? Install the QEMU, right?
Thing is sudo apt install QEMU system x86. I already have it installed, But yeah, just copy these commands, these both commands from the video description, paste them to terminal. And you'll be good to go. Let's go to documents, and you will do these commands, these both commands from the video description, paste them to terminal.
Gonna extract this too. Wow, okay. Damn, that's a lot of C. It needs 9 minutes. Let's just chill here. Maybe let's watch some Roberts is interesting though. Hold on. I'm more interested in it's this thing actually, yeah.
This video was sponsored by Brilliant. Computers operate on a very simple principle. They run instructions one by one. Running each instruction requires several steps. Fetch the instruction, decode it, and execute it. But the question that often puzzles people is, how does the computer know to first fetch, then decode, then execute, and repeat this process in that order over and over again? The simplest answer to this question is the clock. A little device that produces an oscillating signal, which, working in concert with a few logic gates, orchestrates the computer's step-by-step progression through each instruction. Hi friends, my name is George, and this is Core Dumped. This video is not about how to implement clocks, but rather why the oscillating signal they generate is so important to computers. There's a great video from Ben Eater on how to implement a clock like this one. A clock signal can be thought of as a series of pulses, so it makes sense to think that each pulse prompts the processor to move one step forward. Our goal today is to learn how. As always, there are multiple ways to approach this, and I'm not going to present the best one, but the simplest and most intuitive one I could think of. Let's start by analyzing the clock signal. First, it's important to note that clocks can generate many different types of waveforms. We focus on square waves because they take only two values, perfectly matching the binary nature of computers. Now, one aspect of the clock signal that is particularly important is the edges, the tiny portions where the signal switches from one value to another. When the clock signal changes from 0 to 1, we call it a rising edge, and when it changes from 1 to 0, it's a falling edge. The reason we aren't interested in the parts of the signal where the values remain constant is that nothing happens during those intervals. They're like dead zones where no events occur, and there's nothing for the system to react to. But edges are different. For example, we can build circuits that can be used to detect them. At first glance, you might think this circuit always outputs 0. An AND gate only outputs 1 if both inputs are 1. But since both inputs come from the same source and one is negated, it seems impossible for both inputs to be 1 simultaneously.
No way,
But let's
bro.
take a closer look, analyzing the input and the output over time. The input will be the clock signal. When its value is 0, nothing happens in the circuit. It's stable and nothing changes. When the clock flips to 1, the signal propagates to the left, but the inverted signal takes a bit longer to update. For a very brief moment, measured in nanoseconds, the AND gate receives a 1 at both inputs, causing it to output a 1. A fraction of a second later, the updated output of the inverter reaches the AND gate, turning its output back to 0. When the clock flips back to 0, the delay from the inverter occurs again, but this time it doesn't affect the output. And nothing significant happens until the clock flips to 1 again. The delay from the inverter once again causes the AND gate to output 1 for a brief moment before the inverter corrects the output, dropping it back to 0. If we observe the output of this circuit over time and compare it to the clock signal, we see something clear. A quick pulse is generated at every rising edge of the clock signal. In other words, we've created an edge detector, a rising edge detector. There are other types of edge detectors, but we are not going to go down that path. Instead, let's talk about flip-flops. But first, a quick message from Brilliant. There's one fact we all know about traditional studying. Reading books might not always be the most effective method. Act with examples and improve your problem solving is the ALU, short for Arithmetic Logic Unit. For those who are new to the channel, an ALU is a component that receives two binary data inputs and an opcode input. The opcode tells the internal circuitry which operation to perform on the two input values. The result of that operation is then placed on the data output. This component is more general purpose because it no longer performs only one task. Instead, it can perform one of several possible operations depending on the instruction it receives. But how does it do that? Well, some time ago, I showed you a very simple way to build an ALU. But let's not get too far ahead of ourselves. Before talking about circuits, I want you to think about something. In software, when we are presented with a problem to solve, there are usually multiple ways to solve it using different algorithms. We have a term for each of these solutions, an implementation. A single problem can be solved correctly using multiple implementations. The same is true in the hardware world. A hardware component can also be implemented in different ways. Even a component as fundamental as an XOR gate, for instance, can be built using different configurations of more basic logic gates. This is the basic idea behind architectures. In a very vague and simplified sense, an architecture is to hardware design what an algorithm is to software design. Now let's continue talking about the ALU. How could we implement a component like this? How could we even tell a circuit to perform one operation instead of another? Well, as I just mentioned, there can be multiple ways to do it. The simplest approach is this. Because the ALU must be able to perform multiple operations, we can use multiple purpose-specific components to perform each operation. The opcode input can then be passed to an internal binary decoder, which selects the desired operation. Each operation is encoded as a specific sequence of bits. In this example, only 2 bits. 00 means addition, 01 means subtraction, 10 means bitwise AND, 11 means bitwise OR. If we allow the two data inputs to reach all the internal components, we can use the outputs of the binary decoder to select which component's result is allowed to reach the ALU's data output. And just like that, we have our ALU, a component that receives two data inputs and an opcode that tells it which operation should be performed on those inputs and placed on the output. Now, you might be wondering why I'm talking about this. Well, it's because there are different ways to build this component.